Hello, this is Miss Manasseh. This is my second flip learning video, and this one is on types of radiation and decay equations. So we're going to be covering 7.4, the fact that alpha, beta, gamma radiation are ionizing radiations from unstable nuclei in a random process. We're going to look at 7.5, which is these types of radiation and how they are distinguished in terms of penetrating power and ability to ionize. We're going to look at basically the decay equations and the effect on the EdExecl notation that we did in video 1 from each of these types of radiation. Okay, so this really links into what I did in the first video. What is radiation? Well, if nuclei are unstable, they give out radiation to become stable. If you want any more information on what causes nuclei to be unstable to begin with, go back and watch the last 5 minutes of video 1 from roughly 11 minutes 50 seconds into the video. Okay, so we're starting where I left off. So unstable nuclei give out radiation to become stable. This process is called radioactive decay, and there are only 3 things a nucleus can do in order to become stable, and that is give out either something called alpha or beta or gamma. Okay, so the first thing is, irrespective of which type of radiation it is, all radioactive decay is random and spontaneous. What we mean by random is it's linked to likelihood and probability. So what I mean by that is, if I've got 100 radioactive nuclei, I could say, okay, well, one of them will decay soon, but I wouldn't know which one would be first. I could say, okay, probably 10 of them will decay in the next minute, but I wouldn't know which 10 that would be. Radioactive decay is also spontaneous, which means it's not dependent on external conditions. So you can heat up radioactive atoms, you can cool them down. It doesn't matter if they're acids or alkali. Anything external will not affect how radioactive the nuclei are. So spontaneous means not dependent on anything external. So what we're going to do is we're going to go through the types of radiation one at a time, and we're going to try and answer these key questions. What are they? We're going to try to say their mass and their charge using the atomic notation I explained in video 1. We're going to look at how ionizing they are, how far they typically would go in air, what substance stops them, so that is what we meant by ability to ionize, and also what substance they can pass through, so that's what they meant by penetrating power, this column in the spec points. Okay, so we're going to start off with alpha. An alpha particle is made of 2 protons and 2 neutrons. What that means is it's just like a helium nucleus. It's like helium but with no electrons. So another way to describe that is a helium nucleus. It's made of 2 protons, each of those has got a charge of +1. It's made of 2 neutrons, each of those has got a charge of 0. So in total it's going to have a charge of +2. It's made of 2 protons, each have got a mass of 1. It's made of 2 neutrons, each of which have got a mass of 1. So it's going to have a mass of 4. In terms of ionizing ability, I'm going to come to that in a minute, but I want to write alpha in EdExecl notation. Again, this is covered in video 1. So A is mass, Z is the atomic number, and X is the chemical symbol. So the chemical symbol here, we can either write helium, because like I said, this is like a helium nucleus, or we can write the alpha symbol. Whichever it is, it's made of 2 protons, so the atomic number at the bottom there is 2, and the atomic mass we've already said is 4. Okay, so we're going to unpick ionizing ability a little bit. So when we say ionizing ability, just go past those first. The first thing we need to think about is, what is an ion? Well, an ion is an atom that has lost or gained electrons. So when we say how ionizing is alpha, what we are asking is how good is alpha at making other atoms gain or lose electrons. So what I've got down here in this diagram is an alpha particle over here with my 2 protons and 2 neutrons, giving it a +2 charge, and I've got an atom down here. Okay, you can see clearly it's an atom because it's got 4 protons and 4 electrons, making it neutral overall. So if that alpha whizzes past the atom, what it actually can do is attract a negative electron out of the outer shell of the atom, causing the atom to become an ion. It's no longer neutrally charged. So in terms of how ionizing alpha is, we say it's strongly ionizing. That's the phrase we need, and that's because of the fact that its charge is +2. Now, the ionizing strength links to what alpha can travel through and what is stopped by alpha. When it ionizes, it loses its energy, so it stops. So because alpha is strongly ionizing, that means it is easy to stop. So I'm going to go back to the table I had in the previous slide, and we're going to fill in the rest of the row for alpha. Okay, so alpha, we have just said, is strongly ionizing, and what we've said is that means it stops easily. So it only takes about 3 or 4 centimeters of air to stop alpha. It's also stopped by some other very thin substances. In terms of a non-biological substance, it is stopped by paper. In terms of a biological substance, it is stopped by skin. You don't really need to know what alpha can penetrate, but it can penetrate through less than 3 centimeters of air, so 2 centimeters of air, and also mica, but I'm not going to fill that in the table. So now that we've talked about what stops alpha and what allows alpha, what will let alpha through, we're going to go on to talk about alpha decay equations. Okay, so in terms of alpha decay equations, we need to again write alpha using our EdExecl notation. So 4 at the top, apologies that's not very clear, and then 2 at the bottom. First of all, we're going to do an algebra version of this equation. Now I've started off with my original unstable nucleus here in EdExecl notation. If it gives out alpha, the first thing I would always do is fill in the alpha bit of the decay equation, so I wouldn't necessarily answer it left to right. Every single alpha particle has got an atomic mass of 4 and a atomic number of 2, so then fill those in, and then we've got to think about what it will do to the EdExecl notation. Now there's 2 rules that are going on here. At the top we've got something called conservation of mass. Again, this is something you should know from chemistry. Mass cannot be completely destroyed, so all of the mass must go somewhere. So if we start off with a mass of A and four parts of it go into the alpha, what we've got left is A minus 4. We're going to do the same thing for the numbers at the bottom, but when we're doing decay equations, this one at the bottom is called conservation of charge. So we're kind of not being as strict as this being definitely the number of protons, but we're talking about the charge here. So if we started off with a charge of Z and we lose a charge of 2 to go to the alpha, what we've got left is Z minus 2. So the final little bit here, and you wouldn't actually have to really worry about this as an exam, is we know from what we talked about in isotopes in video 1 that the Z number, the atomic number, determines which element it is. So if this has gone from having an atomic number of Z to an atomic number of Z minus 2, it's not the same element. So instead of writing chemical symbol X, I'm just going to put Y. I just mean it's a different element now. So what I'm going to do next is I'm going to do one example of this in numbers, and then I'm going to allow you to pause the video and see if you can manage to do it yourselves. Okay, so the top example here, radon is decaying. If it's decaying via alpha, the first thing I'm going to do is put in the alpha. Remember, don't have to go left to right, we're just going to do the easiest thing first. As soon as I put in the alpha, I know that alpha has got an atomic number of 2 and atomic mass of 4. Then I've got to think about conservation of mass at the top. If I started off with a mass of 222 and 4 of it's gone to alpha, what am I going to have left? 218. Do they add up to 222? Absolutely. So we know that we've done that right. Then we do the same at the bottom. Conservation of charge. We started off with a charge of 86. Plus 2 has gone into the alpha. So what do we have left? Plus 84. And in the question I've told you, yeah, that's a different element. And we can sanity check our work very easily that we haven't made any mistakes. 2 plus 84 is 86. Correct. 4 plus 218 is 222. Correct. Okay, so pause the video and then resume it when you've had a go. Okay then, so first one. First thing I'm going to put in is, it was alpha decay, so I'm going to put in the alpha. As long as I know it's alpha, 2 at the bottom, 4 at the top. Then I've got to fill in the remaining numbers. So conservation of mass, what do I add to 4 to make 133? The correct answer is 129. Conservation of charge, what do I add to 2 to get 55? The correct answer there is 53. Final example then, if it's alpha decay, first of all fill in the alpha, then the 4 and the 2. Conservation of mass, what do I add to 4 to get 195? The answer is 191. What do I add to 2 to get 78? The answer is 76. The only other thing you could do differently here is, remember, instead of writing the alpha symbol, I could write HE. So I could have written 42HE in each example, because as I said, alpha is the same as a helium nucleus. But I think it's easier with the alpha symbol personally. Okay, so the next thing that we are going to talk about is, just going to flick back to my table, what is beta? So this is going to be quite counterintuitive for some people, but what beta is a fast moving electron. But this fast moving electron is not one of the electrons that was in the electron shells. It's a fast moving electron that comes from the nucleus. This is all about the nucleus. So I'm going to explain to you briefly, before we move on, how that happens. Let me just flick back again. So what's actually happening in the nucleus in order for an electron to be given out is that a neutron becomes or decays into a proton and an electron. Okay, so if I've got my nucleus like this and one of those nucleons is a nucleus, what that does is that neutron changes into a proton. The proton in the nucleus, but the electron gets emitted. Okay, so that can fire out. How does that happen? Well, this really is straying into A-level territory. Protons and neutrons are not actually fundamental. They can be broken down into smaller pieces, and the pieces in the neutron are not as stable as the pieces in the proton. If you've got any more questions about this, come back and actually ask me as your teacher. I'm not going to spend any more time in the video on this. So what I want to do first is just use the rules of conservation of the decay equation to just show you that this is possible. So I'm going to put in the EdExecl notation for the neutron. So neutron has got a mass of 1 and a charge of 0. A proton has got a mass of 1 and a charge of 1. An electron has got a mass of 0 and a charge of -1. So let's just check with our conservation laws that we did a minute ago that this is possible. Okay, so in terms of conservation of mass, we've started off with a mass of 1 on the left here. On the right we've got a mass of 1 and a mass of 0. So 1 equals 1 plus 0. Absolutely, that is possible. Conservation of charge, we started off with a charge of 0 and we've got a charge of +1 and a charge of -1. Add those up, what do we get? Our charge of 0. So that's absolutely possible. So what's going on in the nucleus is a neutron turns into a proton and that will spit out an electron. So let's go back and fill in our table now that we've talked about that. Okay, so we've said beta is a fast moving electron. The mass of an electron is 0 and the charge is -1. So if we write our beta in EdExecl notation, the mass at the top is 0, the charge at the bottom is -1. Occasionally you'll see this written with an E for electron instead of the beta symbol. Either is fine. I tend to use beta, so I'm going to put 0 at the top and -1 at the bottom. The next thing that we need to do, exactly the same as we did, is to think about how ionizing is beta going to be, and again I've made a slide to help talk you through that. So how ionizing is beta? So I've got my atom here, 4 protons and 4 electrons, so neutral to begin with, and I've got my beta up here with my -1 charge. This time, if the beta whizzes past the atom, it could repel the electron out of the outer shell of the atom, leaving behind an ion. Now, the alpha had a +2 charge, whereas the beta minus has only got a -1 charge. So the strength that we give it in terms of words, we say that beta is weakly ionizing, because instead of it being a +2, it's only a -1. So remember that how ionizing it is links to how easy it is to stop. So if its alpha was strongly ionizing, it was very easy to stop. This is only weakly ionizing, so it's less easy to stop. Okay, so it's less easy to stop. So if we go back to our table then, okay, so we find that beta, as we've said, is weakly ionizing. Its range in air is about 1 meter. It is not stopped by skin or paper, so it can pass through both skin and paper and 3 to 4 centimeters of air. To stop beta, you need a few millimeters of aluminium. So now we're going to do beta decay equations. Okay, so that's our next step, is beta decay equations. Okay, so beta, first thing we need to remind ourselves of is how to write it in EdExecl notation. So we know that the atomic mass is 0, the charge is -1. So first of all, I'm going to do the algebra version, the general equation. So easy bit first is fill in the beta. Once we know it's beta, all betas have got a 0 and a -1. And then we need to think, what's that going to do to what's left? So if it started off with an atomic mass of A and it gives out 0 atomic mass, it's still going to have an atomic mass of A. If it started off with a proton number of Z and it gives out -1, what we've got to add to that to get Z is Z plus 1. So we say, what's actually going on, remember, is a neutron is turning into a proton. So it makes perfect sense that the number of protons here is going up by 1. The number of protons has changed. It's not the same as it was before. So again, we've got a different element. I'm just going to use Y to show, yeah, it's a different letter, a different chemical, it's a different element. So again, I'm going to do one example, then I want you to pause the video and see if you can do 2 more yourself. Okay, so if we've got radon 222 and it gives out beta decay, the first thing I can do is fill in the beta sign. If it's beta, it's got a mass of 0 and a charge of -1. What's that going to do to the remaining numbers? What adds to 0 to get 222? It is 222. What adds to -1 to get 86? The answer is 87. So again, what we did here is called conservation of mass at the top and conservation of charge at the bottom. So now pause the video and see how you get on with those second 2 examples. Okay then, let's see how you got on. So first thing to do is put in the beta. Because it's beta, mass of 0, charge of -1. What do I add to 0 to get 133? 133. What do I add to -1 to get 55? The answer is 56. You can give your 1 mark for the top ones and 1 mark for the bottom ones. Most common incorrect answer is 54, where people forget the minus sign on the atomic number of the beta. The next thing then is beta again. We're going to have an atomic mass of 0 and an atomic number of -1. What do I add to 0 to get 277? The answer is 277. What do I add to -1 to get 108? The answer is 109. So again, give yourself 1 mark for the top, 1 mark for the bottom, and hopefully we got lots of 4 out of 4s. So next thing we're going to do is go back to our table and talk a little bit about gamma. Okay, so in terms of gamma, gamma is something that you will have heard of all the way back in the 3rd year. Gamma is a type of electromagnetic wave. That means it's pure energy. Gamma does not have any charge and it does not have any mass. So if you were going to write gamma in EdExecl notation, it would be 0, 0. So we don't actually write that, we just literally write gamma. Because it doesn't have any effect on the AZ notation, there is no decay equation for gamma. You only need to worry about that for alpha and for beta. But what we do need to know is the ionizing ability and link that to what substances it can pass through and what would stop it. I'm just going to delete my zeros off here because I don't like it. Right, okay, so if we go back to talk about gamma then, when we talk about how ionizing gamma is, first thing we can say is gamma has got no charge and it's got no mass. So whereas alpha could attract the electron out of the outer shell and beta could repel the electron out of the outer shell, it might be your thoughts, okay, well gamma doesn't have a charge, gamma is not at all ionizing, but actually there's one thing it can do which still could ionize. If the gamma is exactly the right frequency and it hits the electron bang on, it can give it so much energy that it has to move out of the atom. I think about this, if you're going round and round in circles on a roundabout and suddenly somebody gave you a lot of energy and made you spin a lot more quickly, what would happen? You'd spin off the side of the roundabout. So it's only possible to keep moving in a circle at a constant speed if you've got a certain amount of energy. If you get too much energy, you can't move in that same circle anymore. So that's unlikely, but it's possible. So what that means is gamma is very weakly ionizing because it's neutral. Because it's very weakly ionizing, what that means is it's very hard to stop. Okay, so that's going to link back into our table. Okay, so we've said gamma is very weakly ionizing. Theoretically, the range in air is actually infinite. There's no theoretical range. It's not stopped by aluminium. You need a much more dense substance to absorb that radiation and get it to stop. So not just a few millimeters, but you need a few centimeters of lead. Lead is very expensive, and because it's a metal, it's also very, very scarce. So sometimes when we're looking for a cheaper alternative, you can use a few meters of concrete. So those are our two options, a few centimeters of lead or a few meters of concrete. So the things that stop beta do not stop gamma. So this can pass through a few millimeters of aluminium. It could also pass through a meter of air, it can also pass through everything alpha could pass through, so skin and paper as well. Okay, so like I said, there's no decay equation for gamma. That's nearly everything for this topic. The only thing is to mention briefly, this learning intention here talks about neutron radiation. Neutron radiation is not given out spontaneously by unstable atoms, but it is something that we're going to meet later in this topic when we talk about something called nuclear fission. So I'm going to explain it here just in the context of decay equations. So sometimes neutrons are given out or radiated when at the same time that a large unstable nucleus splits up. You don't really need to worry about the details of this yet. We'll come back onto that when we're talking about nuclear fission later in the topic. But what you can see here is if this large nucleus is broken into two smaller bits, sometimes it doesn't divide exactly and some neutrons, usually 2 or 3, are given out. So what we want to do is work out what that's going to do to our decay equation. So first of all, we need to write a neutron in EdExecl notation. So a neutron has got a mass of 1 and a charge of 0. The general equation then would be that if we started off with AZX, we can put our neutron in, N for neutron, 1 and 0. What would that do to the number at the top? It would make it go down to A minus 1. What would it do to the number at the bottom? If it starts off with Z, and it would still be Z, and so it's going to be the same element. So I'm going to apply this. This is slightly different to alpha, beta, gamma equations because, as I said, you often get more than one neutron given out at the same time. So can you see here I've got a big number 2? This is telling me, if you see it like this, that 2 neutrons have been given out. So if each neutron has got a mass of 1 and a charge of 0, we've got to analyse what that will do on the rest of our numbers. So first of all, let's look at the bottom number because that's easiest. If each neutron has got atomic number of 0, then collectively 2 of them will still have an atomic mass of 0. So 0 plus 0 plus 86 equals 86. If we've got 2 neutrons and they've each got a atomic mass of 1, the collective atomic mass at the top here is going to be 2. So if I'd started off with an atomic mass of 222 and the 2 neutrons lost 2 of those, what I would have left is 220. It's still got an atomic number of 86 and that's what it started with, so it's the same element, it's still radon. So pause the video, give this a go. Okay then, so here there is no number, so that just means 1 neutron. It is a neutron, so it's got a mass of 1 and a charge of 0. What do I add to 1 to get 133? 132. What do I add to 0 to get 55? It's 55. That hasn't changed, so it's still cesium. Give yourself 1 mark for if you've got the top 2 numbers correct. Give yourself 1 if you've got the bottom 2 numbers correct. Here we've got 3 neutrons. Each neutron has got a mass of 1 and a charge of 0. Okay, so 3 times 0 is 0. What do I have to add to that 0 to get 78? The answer is 78. Doing the top numbers, 3 times 1 is 3. What do I have to add to 3 to get 195? Answer should be 192. The atomic number hasn't changed, so it's still plutonium. 1 mark for the top, 1 mark for the bottom. Give yourself a mark out of 4. And I'm going to go all the way back to the learning intentions for this little section. Whoop. We know that alpha, beta and gamma are all ionizing. They are all from unstable nuclei and that process is random. We also know the penetrating power and the ability to ionize for alpha, beta and gamma. And we've talked about the effect on the mass numbers and atomic numbers for alpha, beta, gamma and neutron, and we've done balanced nuclear decay equations for alpha, beta and neutron. So that is everything for this video. Well done!